Hey y'all, let's do some homework together. This is our first homework of the year, and it's all about limits at infinity. So number one says the limit as x approaches infinity, and then we've got this rational function, and we want to know essentially what is the behavior of the graph as x goes to infinity. So if you imagine you've got your x-axis and your y-axis, and this function is doing something, what's happening to the value of the function as x goes to infinity? So way off to the right, what is this value approaching? So what we talked about in class, and we kind of got pretty deep into the algebra here on why this happens, but just to simplify things a bit here, we really just want to know whether the numerator or the denominator is growing at a faster rate. And to determine that, we're going to look at the largest degree term. And if that's in the numerator, then there will be no horizontal asymptote, and the function will just diverge to either positive or negative infinity. And if the denominator is growing the fastest, the function will just approach zero. And if the degrees on the numerator and the denominator are the same, so that like if you have two quadratics, for instance, and that's as fast as it goes, then you want to look at the leading coefficients. So if we're looking at this one, we see we've got an x cubed on top. This is going to be our fastest growing term. And when that happens, the function is going to diverge to either positive or negative infinity. In other words, it's either going to go up or down. And so to determine whether or not it's going to go up or down, you just want to reason through what the sign of this function will be once you plug in some very large number. So if I plug in a large number into x here, like say 100,000, that's not even that big in the big scheme of things, but then again, any number really isn't. But if I plug in some large number here, 2 times that number cubed minus 1 is going to be positive, and so will the denominator. So this function, as x goes to infinity, is not going to have a horizontal asymptote, but instead is going to diverge to infinity. Number 2. Notice here we've got two quadratics. This is kind of what I was talking about earlier. We have x squared and x squared. So we really want to just look at these two terms. The x squareds will reduce to 1, and so our horizontal asymptote is just going to be 2/3. We don't care about the plus 1, minus 1 in the big scheme of things, because when we plug in some extremely large number, or I guess in this case, an extremely small number, let's say, you plug in negative, like, I'd like to go with 100 million billion just because it sounds kind of funny. But the larger this number gets, the less of an effect, relatively speaking, plus or minus 1 is going to have. Right? Number 3 says limit as x approaches infinity. And then we've got a bunch of stuff going on here. So here, this is not really a traditional rational function here. It's kind of written like a rational function, but technically a function is only rational if both the numerator and the denominator are polynomials, which neither one of these are. We've got these terms that are polynomials themselves, but these little exponential terms kind of get in the way of it being truly a rational function. But what we talked about in class was that certain kinds of functions will grow faster than other kinds of functions in the long term. And exponential functions will always grow faster than polynomial functions. So even though, like, if you were to graph 3 to the x and x to the 99 and looked at both of the graphs, it's going to look like x to the 99 is growing faster. And for quite a while, it'll have a larger slope or larger rate of change. But eventually, this 3 to the x is going to catch up. And that might be worth kind of considering just as a little thought experiment when that happens. But eventually, this 3 to the x catches up and starts going a lot faster. So in the long term, 3 to the x will have a larger rate of growth. So that in the numerator, the only term we really care about is 3 to the x. And the denominator, the only term we really care about is this e to the x. So the question now is like, well, which one's growing faster, 3 to the x or e to the x? And since 3 is bigger than e, this right here is going to be our largest term. And when I say largest, what I really mean is that it has the largest rate of growth. I just say largest to kind of shorten it up a little bit. So yeah, this 3 to the x is going to grow the fastest. And that's going to in the numerator, which means we're going to have kind of the same kind of behavior we have it over here, where it's either going to go to positive or negative infinity. There's not going to be a horizontal asymptote on this one. And to determine that, just plug in some large number here, and we can see that the numerator is going to be positive, and the denominator is going to be positive. The only terms you really need to even consider are the largest ones. Everything else is just not going to have much of an effect on it in the long term. So either way, yeah, this is going to go to positive infinity. Number 4, we've got x to the 1/3 over x to the square root of x. Now, we did work out some problems with square roots, and we'll work out a few more towards the end here. But this is not going to, you don't really need to approach this one like we did the ones in class. Instead, just rewrite these as like x to the 1/3 over x to the 1/2, and now it's a little bit more obvious which one is going to grow faster. X cubed grows faster than x squared because 3 is greater than 2, and in this case 1/2 is greater than 1/3. So since 1/2 is greater than 1/3, this function will grow at a faster rate than this one. So anytime you've got a function, a fractional function like this, and the denominator is growing faster, the overall value of the function is going to approach 0. This is kind of like the bigger on bottom scenario, and we haven't had one like that yet. This is our first one. So number 5, looking at these terms, this is a traditional rational function. We got a polynomial on top, it's linear, and a quadratic polynomial on the bottom. That quadratic is what's going to grow the fastest, and whenever the denominator is growing faster than the numerator, the limit as x approaches infinity is always 0. I guess we'll move to the next column here, up to number 6. Looking at these terms, we've got some quartic terms, but those are merely polynomial terms. This e to the x, this is really what's going to grow the fastest. And so that would be, now let me take a step back here. If we're going to positive infinity, it would grow the fastest. The graph of e to the x kind of looks like this, right? And so as x goes to infinity, this is going to go up and grow really fast. But if x is going to negative infinity, then e to the x is actually going to 0. So this is actually not going to be our quote-unquote largest term here, because as x goes to negative infinity, this term is just going to 0. And so it will be pretty irrelevant. Just like the 32 will be essentially irrelevant. And so the only ones we really want to look at are these 2 quartic terms, and they have the same degree, so they have the same relative rate of growth. And so the horizontal asymptote here will just be the ratio of the leading coefficients, which is 2 over 4. Number 7, we're going to negative infinity. Here's another case where these exponential functions are going to go to 0. So we'll just kind of cover it up with a 0 here. And let's see, what else is going on here? All right, so our largest term other than that is going to be this x to the 5th. That's going to have the largest rate of growth. And so whenever the denominator has the largest rate of growth, the limit as x approaches infinity or negative infinity is just going to be 0. Number 8. That looks very similar to the one we just did. Is it the same? It's pretty much the same. These exponential functions, once again, are going to go to 0 because x is approaching negative infinity. The only thing different about this is that the fastest growing term, this x to the 6th, is in the numerator rather than in the denominator. And so when that happens, we do not have a horizontal asymptote. No horizontal asymptote here. So we just need to determine whether the function is going up or down to the left, right? Which one is it? And so to determine that, we are going to just imagine you plug in some very large negative number here, so like negative 1,000. Doesn't even have to be that big. So if I plug in negative 1,000, this is going to be a positive term, right? Because I'm raising it to the 6th power. Anything to the 6th power is going to be positive. 3 to the x, that's going to be positive. 2 is obviously positive. So our numerator is positive. But in our denominator, if I plug in negative infinity, e to the x will still be positive, but x to the 5th, that's going to be negative, right? So, so this is going to go to negative infinity. Number 9. Number 9 is a little bit of a preview of what we're going to do a little bit later in this unit, when we're going to look at different limit laws. But I did show you one like this in class where you can split this up to be the limit as x approaches negative infinity of 5 minus the limit as x approaches negative infinity of 1 over 1 plus x squared. You could find like a common denominator and combine these and not split it up like that, but I think it's just easier to split it up. So this first one is just 5. It's a constant function. It looks basically like this. It's just horizontal. And as x goes to negative infinity, it's just always going to be 5. So the value of this limit is just 5. The value of this limit, let's calculate this separately. This is a rational function, so we're only expecting there to be one horizontal asymptote here because the denominator has the largest agreed term, or the fastest growing term, this x squared. So when that happens, when the degree on the bottom's bigger, this function approaches 0 to the left and to the right. So whether or not it's positive or negative infinity. So this is going to be minus 0, which is just going to equal 5. Number 10, looking at these terms, we've got x to the 5th on top is going to be our biggest one. That's on top. So we're not going to have a horizontal asymptote here. So we just want to know, going to the left, since this x approaches negative infinity, are we going up or down? Which one is it going to be? So let's just imagine we plug in some very, I guess technically a small number, but like, negative 1,000 or something like that. You don't even have to be super big, but just imagine plugging in some large negative number, which I guess is just really a small number. But so the numerator is going to be negative. The denominator, so this is a negative up here. The denominator will be a positive plus a positive minus 1. This minus 1 is pretty irrelevant because these are going to be very large. So we have a negative divided by a positive, and that's going to be negative. So this is going to approach negative infinity. It's going to have this behavior where we're going downwards instead of upwards. Number 11. Now this one's a little different than any of the other ones because it's not a fraction, but we can still reason through it. As x approaches negative infinity, e to the x goes to 0, and x to the 10th gets really big. So you have like 0 times some big number. Well, 0 times anything is just 0. So this is just going to go to 0. Number 12. Good old rational function where the degree on the numerator and the denominator are the same. We don't have any exponential or anything like that going on here. So we're really just going to focus in on these two terms. The degrees are the same, so we really just need to look at the ratio of the leading coefficients here. 12 over 2, which is 6. Number 13, 1 over x. This is just your parent rational function. You should be pretty familiar with this function. It looks like this, and as x goes to infinity, this function approaches 0. You could still reason through it based on the degree of the term, just like we did all the other rational functions, but you should know kind of what this looks like. All right, 14's got a natural log. So we talked briefly about the rates of growth or orders of rates of growth in terms of like what types of functions grow faster. We said exponential functions are going to, in the long term, grow faster than polynomial functions, and polynomial functions will grow faster than logarithmic functions. So if we're just thinking in terms of rates of growth, x in the long term is going to grow faster than natural log. So this is going to be kind of a bigger on top scenario. It's not going to have a horizontal asymptote. It's either going to go up or down. And so it says x approaches infinity, which would be good because natural log doesn't, this function doesn't go to negative infinity. It does have a vertical asymptote that kind of stops it. So we'd have some issues there, that little domain problem. So it's a good thing it's asking for x goes to infinity. But we want to know, is it going up or down? So if I plug in a large number, this is going to be positive, and this will also be positive. So since both of these will be positive, a positive divided by a positive is going to be a positive number. So this is just going to be positive infinity. All right, that's the first page. Let's flip it over on the back. Now we've got some of those square root problems that we worked on in class. Now in class, I showed you how to work these rational functions using factoring. But as you can see, you don't really need to do that if you just analyze the rates of growth of the individual terms. But the reason why I wanted to practice that whole factoring gimmick was because it really helps to solve ones that have the square roots like this one. So for these next few problems, I am going to go through that whole factoring process and really dig through the algebra to make sense of what's happening. So to do that, what I'm going to do is rewrite this limit. Now, as you're writing limits, if you have, I didn't have any intermediate steps on here except for, I guess, number 9. But if you're going to have an intermediate step where you're actually going through the algebra, make sure when you say equals that you write this limit until you actually evaluate the limit. Because if I just say like, oh, this equals negative 3x plus 1 over root x squared plus x, this actually isn't true because this side is talking about the limit, the left side is talking about the limit, the right side, there's no limit there. So yeah, so you have to include that little limit as x approaches infinity. And the AP graders, I think, will be pretty strict about that. So make sure you're showing your work properly. But anyway, what I want to do here is I want to factor out an x squared. So I've got negative 3x plus 1 on top. And on the bottom, I have square root of x squared, which is what I'm factoring out, times 1 plus 1 over x. Now, if I take this square root and I split it up using, well, really it's an exponent property, but we're going to apply it to the square roots. Whenever you have a product underneath a square root, you can break it up and just write the square roots separately. Oh, got a little ahead of myself with the plus minus there. In other words, we can write it like this. And so the square root of x squared is plus or minus x. Whenever you have a problem like this, you're going to end up with 2 horizontal asymptotes. One is going to be positive and one comes from the negative. So we do need to consider like which one are we actually going to work with here. Okay, now the other thing I want to do, and I guess I forgot to do this, is to factor this numerator. And even though it doesn't have a GCF, I can still factor out an x. So if I factor out that x, I'm going to be left with negative 3 plus 1 over x. Okay, so to decide on like which is this going to be? Is it going to be plus or minus? We've got to make this decision, and that all depends on whether we're going to positive or negative infinity. If we're going to positive infinity, like in this problem, this x will be positive, and the 1 over x will be positive. Everything over on the denominator will also be positive. So we're going to go ahead and take just the positive value here, not the negative one. the x's will reduce to 1. Anything that's like 1 over x or where the denominator has a larger degree, those are all going to go to 0. So this is going to equal the limit. Oops, switch colors on you. The limit as x approaches infinity of the x's are going to go to 1. The 1 over x, that's going to go away. So this is just going to be, well, it's just going to be 1. I'll write the 1. You usually don't have to, but I'll write the 1 times -3 plus 1 over x over 1 times the square root of 1 plus 1 over x. All right, so yeah, these leading coefficients are just going to be 1. And so 1 divided by 1 is just 1. We can actually just erase those. We don't really need those. So let's clean this up just a bit here. Okay, so now let's think about what happens as x goes to infinity. As x goes to infinity, -3 is just -3. Right? 1 over x goes to 0, so we have plus 0. In the denominator, 1 is just 1, right? That's constant. 1 over x goes to 0, so we have the square root of 1, which is just 1. So if we simplify this fraction, we get -3. Now if I look back at the original problem, and I see, okay, well, wait, hang on a second. The square root of x squared, that's just x, right? You can kind of think about it as a rational function, right? Like if I just write this to say, oh yeah, if I'm just looking at that first term, -3x is up here over x, we get that -3 right away. This algebra is kind of important though, because there are some, like the plus or minus thing, it can get away from you if you don't take that into consideration. We're going to see that in number 16. But I think if you just like take a quick look at it, you'll kind of get the hang of like where this is going. Like I can just look at number 16 and say that, oh, the square root of x squared is x. So if I have 1 over 1, this is either going to be plus or minus 1, depending on whether or not we're going to positive or negative infinity. Number 17, I can look at this and say, okay, well, once I take the square root of this bottom term, that's going to be 4x squared. And then so the degrees are the same. The ratio of the leading coefficient is just going to be 1 over 4. And then it'll either be plus or minus depending on whether or not this is plus or minus. So it's a little bit of a shortcut you can take once you really understand, what's going on behind the scenes here. But I think doing the algebra is good practice. All right, so let's do the kind of the same thing here. We've got the limit as x approaches negative infinity of x over, and I'm going to just kind of go straight to this step where I split off that term, that x squared, times the square root of 1 minus 1 over x. Okay, the square root of x squared, that's going to be that plus or minus. So we need to decide which one are we going to take, because we are going to get two horizontal asymptotes here. And so because we're going to negative infinity, this is going to end up being -1. So we'll go ahead and just keep the negative. All right, I think we're getting pretty close to go ahead and simplify this. The x's will reduce. There we go. And then so as we go to negative infinity here, this 1 over x is going to go to 0. right here. That's going to go to 0, and so we're going to end up with 1 on the numerator over -1 on the denominator, so we just get -1. And the reason why I'm not writing the limit part like after this step, right, is because this is where I'm actually evaluating the limit. And so that's why this kind of it doesn't get dropped, but it's like like for instance, if you were evaluating a function and you actually you plugged in the number, it's kind of like one way to think about it, and it's kind of bad math here, but one way to think about it is, it's kind of like we're trying to plug in negative infinity into x. Now, obviously, you can't do that because negative infinity is not a real number. It's not even a number. So you can't just plug it in, but that's kind of the concept of what this limit at infinity is. It's almost like if you could plug in negative infinity, this is what you would get. What it really means, though, is that this function is approaching -1 as x goes to the left. There's a horizontal asymptote that the function's approaching. Okay, number 17. Looks like this one's going to go, if I had to guess, it's going to go to -1 over 4. But let's see if the algebra verifies that. So we have x squared minus x over, and then to simplify this, I'm going to split off that 16x to the 4th. Factor that out to get 1 plus 1 over 6. Oh, wait a minute. 16x cubed. So let's go ahead and take that square root. We get the plus or minus. So we have to consider, could be plus, could be minus, but since we're going to negative infinity, we'll go ahead and take the minus. Let's factor out also the x squared in the numerator so that we can do the cancellation process. So the limit as x approaches negative infinity of x squared times 1 minus 1 over x over -4x squared times 1 plus 1 over 16x cubed. Hopefully what you're seeing is that like all this other stuff, like all this stuff is all going to just not really change anything because these fractions are just going to go to 0, and then when you multiply by 1, that doesn't change anything. So this is like, we're just multiplying these by 1 as we get closer and closer to negative infinity. So yeah, let's go ahead and evaluate the limit as x gets, so the x squares are going to reduce to 1, so it'll just be left with -1/4. So it's -1 times 1, which is -1. I'm sorry, so 1 times 1 is 1, and then you have this -4 times 1. So yeah, just -1/4. All right, find the horizontal asymptote, if there are any. The first one is just a plain old rational function. We see that the numerator has a larger degree than the denominator, so here there is none. And let's, usually it's a good idea to say why. So there's none because, well, how do I say this? There's no horizontal asymptote because the numerator grows faster than the denominator. Okay, sine x. Now, it's been a little while since you took pre-cal, but the sine graph does something like this, right? It's a periodic function. This doesn't actually approach anything, right? It's just constantly going up and down and up and down and up and down and up and down. It's not getting closer and closer to any specific value. So this one actually doesn't have one either. None. The function, the way we'll describe this is to say the function oscillates between, I'll be pretty specific here, -1 and 1. For number 20, I'm going to rewrite this kind of, so like I'm going to approach this like I did above. Okay, but let's see if we can just kind of go to the answer a little faster here. All right, I'm going to take out this 25x to the 6th, and I'm going to also factor out the 3x cubed. Or actually, I don't even really need to do that. Let's just leave that in there as it is. So 3x cubed plus 3x minus 2 over the square root of 25x to the 6th times the square root of 1 minus, what would that be, 3 over 25 x to the 4th. So when I take the square root of this 25, that's going to be plus or minus 5x cubed. So 3x cubed plus 3x minus 2 over plus or minus 5x cubed times the square root of 1 minus, and then all this other stuff that we're not really going to care about. So the horizontal asymptotes here are going to be defined by the ratio of the leading coefficients here. So 3 over 5, and it's going to be plus or minus. There's going to be 2 leading coefficients, so we get y equals plus or minus 3/5. So if the question was, what's the limit as x approaches negative infinity? It would approach negative 3/5. And if the question was, what's the limit as x approaches positive infinity? You get positive 3/5. Number 21 is a polynomial function. Polynomial functions don't have horizontal asymptotes. None. Okay. This function, we'll say it diverges. Diverges to, well, to the left it goes to negative infinity. To the right it goes to positive infinity. So I'll just say plus or minus infinity. Number 22 is going to have a faster growing term on the denominator, and so anytime that happens, like when I do that, if I were to do this whole square root business, take it out, square root of x squared is x, and that's going to grow slower than x squared. So anytime you've got a denominator that grows faster, it's always the function will always go to 0. All right, now 23 is a little funky. Cosine x divided by x squared. Now cosine x is another one of these periodic functions. Just like sine, it oscillates between -1 and 1. But if you think about horizontal asymptote as the value as x goes to infinity, if you plug in like some really large number into x here, x squared will be some really large number. So you've got a small number here. I mean, this is only going to ever be between -1 and 1. But this number is going to keep growing without bound. So when the denominator grows faster than the numerator, then this is going to be another case where the horizontal asymptote is just 0. Okay, we've got a couple brain teasers here. It says attempt these trig limits, visualize the graph, can help you reason through these. So let's think about it. So the first one says, what's the limit as x approaches infinity of sine x? Well, we already determined that sine x does not have a horizontal asymptote. It's not approaching a specific value. So the limit as x approaches infinity is not going to exist. And it's also not going to be infinity or negative infinity. It just does not exist. So you can either write does not exist or write DNE. And even on the AP test, it's okay to write DNE. That's a pretty well-established acronym. Number 25 is going to be very similar to number 23, where you have this oscillating function on top, and then on the bottom you've got a function that grows without bound. So since the denominator is going to grow a lot faster, this horizontal asymptote is going to be 0. Number 26, as x goes to infinity, this 1 over x is going to go to 0. This one's a little tricky. So this is going to equal sine of 0, and probably been a little while since you thought unit circle here, but here's your unit circle. When your theta, or your angle measures 0 degrees or 0 radians, the sine value of that angle measure is going to be the y coordinate of this point, which is 0, 1. So it's going to be just 1. So this is going to equal 1. No, what am I talking about? 0, 1. No. Let's back that up. Sorry, 1, 0. The sine of 0 is 0. So yeah, this will be 0. A little rusty on my unit circle there. Number 27, let's think about what happens. So this cosine of x, recall this is just going to oscillate between 1 and 1, negative 1 and 1. So we've got x minus some relatively small number. This is really going to be your irrelevant number. So it's going to be some number we're going to subtract. The x over x is really what's going to give us what we want here. And so this should approach should approach 1. I'm going to approach the ratio of these leading coefficients. I think the graph of this one might be worth looking at. If you get a chance, throw this one in your graphing calculator, or probably better off throwing it into Desmos to get a clearer picture of what's happening. But this is going to be a case where you have a graph, and this is going to be a rough sketch here. But this particular one is going to have your horizontal asymptote at 1, right? The limit is going to just approach 1 on both sides. But the graph does something kind of cool. It comes up like a rational function, like 1 over x, and then it does like something like this. So what this is like a great example of is the fact that it is possible to cross a horizontal asymptote. What's important is that in the long term, the graph is approaching it. So, I think this is a pretty rough sketch, but this is basically what it looks like. This is, I think, worth looking at just so that you can convince yourself that, hey, it is possible to cross over those horizontal asymptotes. So that's it for tonight's homework. Please come and see me or talk to me, email me if you have any questions, you want some clarification, and I will be happy to help you. Other than that, you'll have a great day.